left, Dr. Dave Zubrow, Dr. Mike Konrad, Dr. Bill Nichols, and Mr. Bob Stoddard.
Okay. I don't know where the slides are.
They're coming up.
Anyway, just a quick show of hands. How many of you are involved with program management or cost estimation or have some familiarity? Okay, now no, you got to keep your hand up. Okay, now the next question is, keep your hand up if you know something about causal learning. Okay, good. I'm glad to see at least one person here. All right, so maybe this will be something new for you. We're talking about a research project that we have that's applying causal learning to software control and prediction, and we call it SCOPE. And John already introduced the panel members, so we're going to talk about 3 studies quickly because we wanted to make this interactive. And so think about questions. Now, the first point that I want to make out of this is why causal learning. It's a subset, if you will, or a form of machine learning that's really focused on causal inference. And we thought, well, there are many heuristics, right? Rules of thumb that are used in managing programs, planning programs, doing cost estimation. But what's the empirical foundation for those? A lot of that's done using regression analysis, other kinds of techniques, but one of the weaknesses of regression is that it really doesn't distinguish between causality and correlation. So if you're going to act on those results, then you might be misled. And what we really want is actionable information. So if you start to think about intervening on a program, taking corrective action, then you'd like some confidence that you're going to get the desired outcome. And finally, while the idea has been around for quite a long time, the tooling techniques, algorithms are making this a practical field of inquiry and a way of generating usable knowledge from observational data, which is one of the things that we are very interested in because you can't do a randomized controlled experiment on everything that you want to know. It's just not practical. Okay, so I said I was going to keep these remarks brief, and I did. So now I'm going to hand this over to Mike Konrad, who's the principal investigator for this study, and he's going to summarize briefly the results of the study and then also take a little deeper dive into the very first one.
Thank you, Dave. So as Dave said, we're talking about this morning 3 studies that we did. The first was we looked at a data set for which there were about 40 measures of complexity in a program, and we wanted to know, which of these would drive success in the program. And we looked at this data through different algorithms, and we found exactly one dominating factor: cognitive fog. So I'll be talking about that on the next slide. In the second study, thanks to the U.S. Army, we obtained a maintenance data set, and we looked specifically at releases that fixed or patched information assurance vulnerability alerts, or IAVAs. You would think that the number of IAVAs addressed per month would drive the amount of effort reported per month. It doesn't necessarily. And so that will be what Bill will be speaking about. And then finally, we also looked at a data set, thanks to Rick Kaisman and Selma Sologlu, that looked at architectural pattern violations and whether they introduce security vulnerabilities. An early analysis concluded not. We concluded otherwise. So those are the 3 data sets, some puzzling results. Looking at the first one a little more directly, we asked, what types of complexity drive or impede program success? You will notice there's a graph, which I'll go into more detail in a moment, but I just wanted to highlight three horizontal bands here. This top 8 measures here represent measures available at the beginning of a program. The bottom 7 measures represent measures of program success, different measures of program success. And the middle 8 represent measures available during program execution. And so in her original PhD dissertation work, Sarah Sheard found 3 measures in the upper or middle band that seem to have promise for intervention to improve program success. And we applied causal discovery to the same data set. And what we discovered is that one of the 3 factors that Sarah identified, number of difficult requirements, seemed to have no causal effect on program success. That was the surprising thing. And the third one, cognitive fog, no matter which algorithm we used, even ones such as the one in the dashed line, which I can tell you about afterwards if you like, which isn't supposed to work well with this kind of data, it also found that dashed line a path through cognitive fog to technical performance gap, which means the behavior of the system doesn't match the requirement specification. So cognitive fog is this big dominating factor. Stakeholder relationships, Sarah's number 2 factor there, does play a role in program success. And what's interesting, though, all the arrows from stakeholder relationship type variables, we generally found that they go through cognitive fog. So, if you were a program manager, what might your takeaway be? Your takeaway might be, let me try to be sure that my programs are not in a state of cognitive fog. Cognitive fog means the frequent state that a team finds itself in when it's dealing with conflicting data or cognitive overload. And stakeholder relationships, the nature of stakeholder involvement and the existence of stakeholder conflict both affect that. One more technical note here, you will see edges throughout the diagram. The edges that have an arrowhead, those represent direct causal effects. So the tail of the arrow, so let me pick here on stakeholder conflict, just above me, right there. I'm colorblind. Oh, okay, that's not my excuse this time, but anyway. Anyway, it's just right above me, stakeholder conflict. Whoops. Okay, pretend you didn't see those. Into cognitive fog. What that means is if you hold all other factors fixed and you change the amount of stakeholder conflict on a program, you would affect the amount of cognitive fog and not the other way. So that's what direct causality means. And I'd like to introduce Bill Nichols, whom I had the great pleasure working with for many years, and he is published on results of looking at the personal software process and team software process. Over to you, Bill.
Thank you, Mike. What I want to talk about are some results that we found looking at data that were provided from the U.S. Army. In particular, we were looking at the processing of IAVs, the information assurance vulnerability alerts, essentially patching. So we wanted to know what is driving the number of IAVs that are being patched, what are driving the cost of patching those IAVs. And we had a number of different factors recorded from the data, including the superdomain, the number of services involved, some funding issues like the ACAT, the number of appropriation sources. But the outcomes we were interested in, and let's see, where's the pointer here?
Couldn't find it.
You couldn't find it? Well, I won't bother then. The important things we're looking for are circled, the IAVA per month and the effort per month. The arrows indicate that there were a number of causal relationships that appeared when we searched this data. However, only a few actually went into our outcomes of interest. Interestingly, the funding factors, appropriation sources, number of appropriation sources in the accounting category appear to drive the effort per month. Curious. A little more intuitively, the superdomain and the number of IAVAs per month drive the effort. Okay, that makes sense. Now, a funny thing happened. The way these arrows are constructed between superdomain, IAVA, and effort per month, it really doesn't mean anything to you, I'm sure, but it suggests a possibility of what we call a Simpson's paradox. And in fact, what happened was when we controlled for the superdomain, the effect between IAVA and effort per month vanished. Now let's be clear on that. There was an effect when you looked at all of the data, a very clear effect. You control for the superdomain, and every individual superdomain, there was no statistically significant effect. That's an important finding, and it just disappears, and it becomes very clear when you look at the causal model. In fact, the appropriations count and ACAT have a similar type of pattern. We haven't looked in detail at whether they go away, but they raise other issues. The ACAT and the appropriations count were persistent across all of the superdomains. What could the funding factors be doing to drive things? So that makes us suspicious that there are other factors that have to be looked at. So among the work we have to do is go back to the drawing board, talk to the subject matter experts, and try to collect some more data, try to tease out what's really going on here. Because what seemed to be obvious from the initial data isn't really obvious at all. Let's see. With that, I'll pass this on to Bob Stoddard, who is going to have some other interesting effects when you start looking, decomposing the data into some of the subgroups.
So this one slide summarizes a causal study we've been doing with Dr. Rick Kaisman, looking at architecture pattern violations driving security. Our journey in research collaboration with him began over 3 years ago when we were looking at architecture patterns driving quality outcomes. So this year, the question was about the security outcome, and we're looking at a file level. And as you can see here, our study was on the Chromium system from an open source system. So we looked at Chromium as a single population, and then 5 of the architecture partitions, as you can see across the column headers. And our factors that we studied are on the left. We have them layered. So the layers are general notion of hypothesized causality flowing downward. And so we have exogenous factors. And then we have the layer 2, the factors that we're most interested in, the architecture pattern violations. And then interim outcomes, and then the final outcome is the security outcome related to that file. So just a note here is that on the bottom row, you can see we are modeling a rare event situation. For Chromium in its entirety, only about 3% of files had a non-zero measure of security outcome involvement. And so that rare event situation, we believe, tripped up and made it more challenging on previous earlier statistical analysis of a relationship between these architecture pattern violations and security. It was inconclusive. So the way to read this chart is that if you see a green cell, that means our causal search had direct causal evidence of that factor to the security outcome. The orange cell represents that there was evidence for an indirect causal relationship, and a red cell highlights the fact that there was not causal evidence of a linkage of that factor to the security outcome. So the takeaway here is that of those 6 architecture patterns, I'm amazing in this rare event situation, the search algorithm still picked up on some causal signals. And specifically, a takeaway you could go with on this study so far is that if you were wanting to introduce a policy about enforcing these architecture patterns, probably clique and modularity violation would be the 2 that you might look at and consider for that policy. As you can see, if you have a correlation study that might say things are correlated, but there isn't a causal basis, and you go and enforce a policy on something that really won't change the outcome, you actually could be doing harm to the situation. So in conclusion, we are firmly convinced that causal learning will accelerate and offer a lot of promise in software engineering research across many topics in that software engineering research. And by confirming arrows or debunking conventional wisdom of arrows, we are hoping to inform when stakeholders should take action. And we believe that often the wrong things are being measured and actions are being taken on wrong signals, mainly on correlation only. So we think there's a lot of promise in continuing to look at quality and security outcomes. We also are going to add into the mix the actual causal estimation of these arrows and use additional machinery to quantify those causal influences. So we need your help. We need access to data. We're looking for people to collaborate by providing data, learning this methodology and conducting it on their own data. We do both. We just think there's a lot of promise in this causal learning.
Thank you. Do we have time? We have time for some questions. So if you have any questions, you wrote it down on an index card, that would be fine to pass it to us, or you can raise your hand and we'll ask.
Okay, well then. We come prepared. Mike,
He didn't tell us about this.
how's causal learning different from machine learning?
So how is causal learning different from machine learning? Well, causal learning is a form of machine learning. If by machine learning you mean producing a model that can be used for prediction from a data set. What's different about causal learning is its focus is on modeling the data generation process. How did the data come to be the way it is? What is driving what? So of particular interest are things like conditional dependencies or independences, such as, hey, if I know what the temperature is outside, I can find that the number of shark attacks and ice cream sales are indeed independent of each other.
Okay, I gave you a chance to think of some questions now. And by the way, listening to Paul this morning, this is maybe the antithesis of generational diversity. Yes, sir.
By causal learning, you mentioned the word repeating.
Yes.
Did you consider, what Professor Judy Pearl was writing about,
Absolutely.
Yes.
right, counterfactuals, intervention, what if not, and caught, and so you're using
Yep.
all that philosophy for this
Yes.
arrow B.
Correct. And I'll just point out, because I was remiss in not doing this earlier, that much of the work that we're doing is really owed to the excellent philosophy department here at CMU. David Banks, Madeline Gleemore, Kun Zhang, and you have Joe Ramsey up there who does a lot of the actual algorithm programming. We're working very closely with those folks on the development of not only the tooling, but also the methodology that we're developing to apply the tooling within the DoD space.
With all those wonderful algorithms, what is your validation
Ah.
approach? Because one way you can say, well, we take a look, makes sense.
Right.
Or you say, well, looking at all the data, matching the algorithm, they're all good. We're using a combination of both.
That's a great question. Do you want to answer it? One of you guys? Or
Yeah,
I'm talking a lot.
Well,
Go ahead.
there are a couple of things that we have been doing. Among them, if we go back to this, for example, one of the things that we've done is we've examined the data with different algorithms. This particular example, we lost the legend at some point, but the dashed line and the solid line represent two entirely different algorithms that were performing the search. So one of the things we've done here is we've demonstrated that separate algorithms are finding essentially the same result. That doesn't happen all the time. Another approach we've used is bootstrapping, where we will we will resample the same and see characterize how often we get the same sets of vertices and edges. Anything you'd like to add to that, Mike?
Face validity, as the gentleman mentioned. We bring subject matter experts and say, this is what we found. Does it make sense? And in our early explorations, we sometimes heard, that's strange.
But it's very easy to rationalize. You can make up a story about almost anything.
Right.
And it is challenging, but one of the pieces of work we're going to be doing this upcoming year too, as it said in the conclusion slide, is taking these graphical models then and actually estimating them. And so then we'll have a sense of how well they at least match the data. So we have both the intuition of the experts as well as the data. But in some cases, as was noted, we may be measuring, the data may be measuring the wrong things. And, right? And the algorithms aren't necessarily going to help us, which is one of the points about using directed acyclic graphs and causal inferences to think about what are the unmeasured influences and how might they perturb the results.
And just to build on that point, that's one of the things we're seeing in this particular graph where there are some hints of unmeasured variables that are confounding the results. And that's why we have to go back. And the algorithms are by and large constrained to the variables, the factors that are available. So we have some additional work to do to try to enrich that set.
Sir.
This year you're working with Army and IAVIS, as you're working to FY20 what are the sponsors and what are the specific problems? Are you going to keep on working with IAVIS, thinking through that stream of thinking, or go on to other sponsors?
You don't always look at me.
Okay, well, so first of all, there's a couple classified programs in which we use this technology, which unfortunately I can't tell you more about. But we, fortunately, some of our collaborators, Bob mentioned Rick Kaisman, Selma Suluglu, Cheryl Jones in the case of Bill's data set of the U.S. Army, Sarah Sheard. So it's frankly, by getting to meet people like you, we do want to go look at some individual and project performance data, technical performance, cost schedule, in particular cost, but quality. That anyway, I think.
So
I think
we're in
the
the
other thing I was-
second year of a third-year research project sponsored by Bob Bonneau and OSD. And the data sets, we just recently obtained one from a static analysis company in Europe that provides nightly snapshots of the code base. And so now this is giving us a way of starting to look at quality data, because trying to get data on defects is difficult from anybody. But yeah, we're open and would love to talk with you more.
Yeah, we're using this in jet engine, predictive maintenance, in other weapon platforms, in the cost community, in system engineering community, acquisition community.
All right, thank you very much, appreciate it.